Today we move into chapter 5 where we learn the graphs of sine and cosine. First of all, it's a very enjoyable chapter that is one of my favorites to do, but it's also an incredibly important chapter. Once you learn the graphs of sine and cosine, they really are helpful in making calculations. The unit circle is an amazing tool, but the graphs of sine and cosine can often give you values without even looking at a unit circle. So let's begin. What's going to be really important today is that you have the PDF notes in front of you. I won't finish every last detail on the whiteboard right here. You'll have to be looking at the PDF notes, and you can pause the video whenever you need. So when we start graphing sine and cosine, number one, what we are going to do is we're going to take a look at what does the graph of y equals sine x look like. Now, first of all, sine, yes, it's a trig ratio. It's been opposite over top of hypotenuse for a long time, and recently it's y over r. But it is also a function. It's a function that relates an x and a y value. Therefore, you can get a graph, just like you can have a parabola, absolute value graphs, square root graphs, and so on. This actually will be the sixth graph in the run of 10 graphs that I'm going to demand that you guys memorize, especially if you're going to take a calculus-based course. So to begin this, what we are going to do is set up a good old table of values. In the old days, you guys have done this before. You've done it as early as grade 10 when you were learning what the graphs of lines look like. And if you remember, you had an X and Y chart, but just turned vertically, and you had numbers like -2, -1, 0, 1, 2 for the X value, and you were finding Y values. We are going to do something very similar. Now, first of all, we are cheating. What we are supposed to do is graph this guy in radians. If you think of the x and the y-axis, we typically don't put down degrees down here. They would be numbers like 1, 2, 3, 4, 5. However, it would make it very awkward, very cumbersome. What we're going to do to get the graph is just to do a quick cheat. And we're going to plot a set of points. And we're going to observe what the graph is going to look like. And just like the unit circle, this is going to be one big pattern. So to start off with, what we are going to do is we're going to say, here is 0, but instead of calling this 1, we'll call it 30 degrees. The cheating is we're going to graph this in degrees, even though we're supposed to do it in radians. The degrees will just make so much sense, and it'd be easy to do. Now, you could use your calculator to double check me, or you can just go with what I show you guys and what's in the PDF notes. What we would do is we'd put up here a height of 1, and each of these dashes would be 30 degrees. So we would be doing it in 30-degree intervals. So 30, 60, 90, and so on. Now here's how we'd begin. What I would challenge you guys to do if we were face-to-face in class is I'd say just have your calculator out, have it in degree mode. The only time you ever really need to change your calculator is when you are in AP Calculus. Then you'd have it in radian mode always. So we would just type it in. You'd put in 0 and you'd say, what is the sign of 0? You'd hit equals and it's a 0. And what would be happening is you'd get a plottable point. Then we would shove in 30. We would put 30 degrees in for the value of x, press sine of 30, and at 30 degrees, that's this first dash, we would get a height of 0.5. We'd put in 60 degrees. Now at 60 degrees, this one came out to be quite a long decimal, and we rounded it off to 0.87. So you would just approximate about where it is, and then we get a perfect one. Putting 90 degrees in, sine of 90, would come out to be a perfect 1. You could confirm it in your calculator. You could even look at your unit circle. And then again, if we were face to face, we'd probably only use the unit circle we'd probably only use our calculator one more time. I'd get you guys to type in the sine of 120. You would all see that it is 0.87. And then I would tell you guys, just like the unit circle, it's one big pattern. And I would get some guessing. I'd say, guess what the next value is. And most people would be like, it's 0.5. And then I'd say right here is 180 degrees. What would be the sine of 180? No typing it in, no using the unit circle. Most people would look at the way this pattern is going and they would realize it's a height of 0. And then the next one, and you can see it in the PDF version of the notes, the sine of 210, either you're going to get it right on the first try or you'd get it right on the second try. Many people would yell out, it's 0.5. And I would say, no, it actually goes down to -0.5. Then negative 0.87, -1, -0.87, -0.5, and then finally you're back to 0 at 360 degrees. And then this is what sine looks like. I've even done it in front of you guys in the class. You might be thinking, geez, this feels like physical science, waves, and you're totally right. This is the math version of the waves. If anyone ever wanted a career in any of those areas that required the waves from Physics 20, also known now as Physical Science 20, you would want to know the math version, the sine and cosine. So this is what the graph looks like. Now, once we were done this, what I would then do, and I would have the boards, I wouldn't have to be erasing, is I would show you guys that that's not the end of the story. There's quite a bit else. What is also there for this graph, and let me just redo it really neatly, I didn't even make this big enough, is the graph of sine, and then cosine in just a moment, goes forever. What happens is we just have done this from 0 to 360. And you never ever tick things off again. Hopefully I'm not ticking you guys off. This is what is called one period of sine. Period means just one complete cycle. And again, if you've taken physical science already and done the waves, you'd be recognizing this. This is 360, but it doesn't end there. In the chart that you guys see in your notes, the one that I just erased, you could keep going. You could put in 390, 420, 450, and what happens is this guy, it's just one giant repeating pattern. And you can even go backwards. You know you can have negative angles like negative 30, negative 60, negative 90. So here is what actually happens. The graph of sine does resemble a wave because the sine is just the math formula for the graph of a wave. And when you have sine just all by itself, there are some very, very important values, and you can see this down on the side of the PDF notes. It does go forever, forward and backward. So the domain would be all real numbers. Remember range is talking about the y-axis? Well, it goes from a height of 1 down to negative 1. So y always goes between negative 1 and 1. The maximum height this graph ever goes is a positive 1. The min value is a negative 1. And the amplitude, again, the physical science people would be like, Jesus, feels like the back of my hand. If you've never taken physical science, well, then this is a little new. Amplitude, the second important definition of the day, is from the middle, how high up and how high down or low does it go? Well, it's 1. It's just a distance of 1 up, 1 down. So the amplitude is kind of wrapped up in the max and the min at this point. Now, this is a very important one. The period. Period is how long it takes for one complete cycle. This was 360 degrees, but remember, we're cheating. We have to answer it in radians. In radians, it's called 2 pi. And so we're going to say both of them for a little while, and then eventually we get to it. So then where would this be? 720. This would be a negative 360, and then there'd be a negative 720, and it goes on and on and on. A couple of easy ones. The y-intercept is simply a value of 0. Now, if I said to you guys, how many x-intercepts are there? The answer would be infinitely many. It keeps crossing the x-axis over and over and over. For right now, we'll just put it down as a pattern. We'll say it's at 0. This right here would just be 1 pi, 180 degrees, 2 pi, 3 pi, 4 pi, 5 pi, and so on. So we just went dot, dot, dot. Now, when we do the graph of cosine, if we were doing this full-on face-to-face in class, we would go back to a table of values and we would plot numbers in. And here is one of the key things that you would realize. Cosine is very, very related to sine. Very related. We always do them on the same day. And this is what you would see if we plotted points. You'd actually see the cosine of 0 starting at 1. And then it would go down to the 0.87, 0.50, negative 0.5, negative 0.87, negative 1. And we would keep the repeating pattern going. The graph of cosine in just one period looks as follows. And this would be where 2 pi is. Down here in the middle would be where 1 pi is 180 degrees. Again, we could do the exact same table of values, plug in numbers, plot, but you only do that at the start. You never plot again. After you're done this, you always freehand draw the graphs. Now, the graph of cosine, to the untrained eye, actually does look exactly like the graph of sine. It goes in the same pattern. It's just kind of moved over a little bit. Hey, think wall and window a little bit, but don't let your mind run to a scary place. The graph of cosine then has so many of the same values as what the graph of sine does. The domain is still all real numbers. The range is still from negative 1 to positive 1. The max value is a 1. The min value is a negative 1. The amplitude from the middle, how much up and down does it go, is still a 1. How much does it take for one complete cycle? that is 360 degrees, or 2 pi. Again, the only differences would be the intercepts. Instead of having a y-intercept of 0, cosine, okay, this was the graph of cosine. Cosine has a y-intercept of a positive 1. And then the x-intercepts, well, that's a little bit different. If here is 180, even though I'm not the neatest person in the world, you guys know that, this would be 90. This would be 270. And then what I wrote in the PDF notes was the radian versions. 90 in radians is pi over 2. And 270, I always forget this one, I always have to look it up, is 3 pi over 2. Now, where do we go from here? You never ever replicate those charts. If we were doing this and making up a study sheet for an exam, you would not put that table of values with 0s, 30, 60, 90. What you would end up doing, and this is not in your notes, is you would memorize this. Just like we memorize certain things like, this for the good old days. You would memorize that sine starts right here in the middle. Don't say 0, say middle for right now. Goes up to 1, down to -1, and repeats itself at 360, or 2 pi. Memorize that cosine starts up at 1, up high. Say up high. And then repeats itself again at 2 pi, or 360 degrees. That is what you guys are going to commit to memory. Now, number 3 in your notes, there is a set of examples where right away, even though it feels like you're not ready for it, we can start to change the values. So if we had y equals sine x, if that was all that there was to it, well, that's the graph, and then we'd be ready to finish the chapter. But there's more. You can actually change how high up and far down it goes. Sine all by itself always goes up to 1 and down to -1. I'm going to say that a whole bunch of times to help you guys remember it. Well, this is actually not going to be hard. Let's say I wrote down y equals 2 sine x. I had a 5, I got to get it to a 2, so it's like the notes. And then I said to you guys, well, what does this graph look like? I'm going to tell you straight out, and it's going to come really quickly. We know what the graph of sine looks like. When you put a 2 in front, and it's going to have a certain letter, remember all those A, B, C, Ds, H, and Ks? This right here is going to affect the amplitude. And in the next lesson, we'll write it down formally. For right now, let's just get used to the idea. What would happen is, instead of going up to just 1 and down to -1, the graph of sine would go up to 2 and down to -2, and then still repeat itself at 2 pi. My apologies for my messiness. This graph is supposed to be symmetrical. This is supposed to be the exact same size as this. And then with the next example, there's going to be so many things that jump out where you guys are like, geez, I've seen this before. So let's say we had a 3 down. Well, then you're like, oh, I know, it goes up to 3 down to -3, and you're right. And you're also right knowing what this does. We've seen this before. When we put negatives in front of things, it turns them upside down, and I can barely get my hands to do it. Here is what this graph would look like. We memorize that the graph of sine starts in the middle and then goes up and down, but wait a minute. This time it's going to go to 3 and to -3, but instead of going up first and then down, it's upside down. It goes down to -3 and then up to +3 and then repeats itself at 2 pi. So what we are going to do all along, unlike what the textbook sometimes does, is we are going to just graph one period. Okay, just one straight period. Go with the textbook if they ever say graph 2 periods, but we're just going to stick to one because we're not using graphic calculators. Now, so what we've done is we've done a vertical stretch. You could even do a compression if you wanted to, and the compression, I'll show you guys with a cosine. Let's say you had the graph of y equals 1/2 cosine x, and we were supposed to say what it looks like. Well, first of all, cosine goes up to 1 and down to -1, and we memorize the basic look of it. If you put a half in front, what it does is it changes the amplitude. Instead of again starting at 1, it would actually start at a half and go down to -1/2 and then still repeat itself right here at 2 pi. So if you were going to say what is the max value this time, it would be a half, the min value -1/2. That's what the number in front does. Now, for our ending one, and don't worry, in the next day's lesson, we'll repeat this and we'll get in the formalities behind it. There is some formal notation, but it won't scare you. You guys will feel like you've known it all along. All of that work in chapters 1 and 2 with wall and window up and down will pay dividends. Let's say you had to graph this. Now notice how there's a 4 and it's not in the same spot. Now this is again just a first introduction, so don't panic. When you put a number in this spot, if you really remember chapters 1 and 2, that actually was the B position, which again we'll write down next day. And what it did was it compressed or stretched horizontally. So how are you going to do that in sine? Well, we're going to do a little bit of a cheat, but not as much of a cheat as the graphing in degrees instead of radians. If right here was 2 pi, that's where sine normally repeats itself. This value changes it. And it's actually going to be the fourth time in your mathematical life it is different. It's opposite what you're thinking. You might be thinking it goes 4 times wider, but it actually goes smaller. And here's how we'd actually do it. The period is how long it takes to repeat itself, and until this moment it's always been 2 pi. What we do when there's a number other than just a 1 in front of the x or the variable symbol, the theta, is we divide it. We go 2 pi divided by 4, it would be 1/2 pi. And so what it means is we're going to squeeze this guy down into a quarter of the length. So instead of being at 2 pi or up here 2 pi, we're going to like really compress it. Okay, so it'll be in a quarter of the distance. But then here's what we're not going to do. We're not actually going to do this guy here by saying here's 2 pi, here's 1 pi, here's a quarter, and then do it. What we do is we just simply say, okay, sine goes up to 1, down to -1, and then repeats itself. And this right here is going to be at a 1/2 pi. It's kind of a little bit of a cheat, but it's one that everybody in every textbook does.